So I've noticed that a lot of people seem to have some trouble understanding exactly how two force bodies work and like how to properly analyze them in a like mechanics question. And I think it's really important. Like it's probably the most important part of our class. I think that's even what our professor told us. So I'm going to try and help explain what a two force body is, how it works, and how it like why it matters for our mechanics problems. And so hopefully that can help you guys with the midterm tomorrow. So, okay, so two force body, obviously, or hopefully it's obvious, it's a body. So in this case, our demonstration, the body is this ruler that has two forces. So generally that would be a pin connection at one end and a pin connection at the other end. That's our two forces, right? Because each pin applies a force on the body. Obviously, technically in real life, there's a third force, and that's the force of gravity. This ruler weighs something, but for the sake of our demonstrations, we're gonna assume that this ruler does not have any weight. And also in all the problems that we're doing for the midterm, at least all the problems on the practice midterms, we always assume that it's weightless. So these demonstrations will apply to the midterm questions. So there's two important things to understand about two force bodies. Actually three important things. The first two are like a prerequisite to understand the third. So first thing to understand is that the two force body, not just the two force body, actually everything, right? This applies to everything, but right now we're talking about two force bodies. They are in equilibrium. We're only talking about equilibrium. Like obviously in the real world, that's not the case. Like things can move in the real world, but for the sake of these problems, we're talking about equilibrium, which means they don't move. Now that probably sounds pretty obvious. That's kind of been the point of like everything we've been doing in this class, but understanding what that actually properly means for solving these questions is pretty helpful and will prevent you from making some like obvious mistakes. So, okay, let's say, again, we have this two force body. We have a pin connection at one end and a pin connection at the other, right? So let's say, for instance, that at this end, I'm gonna start pulling. I'm gonna put the ruler in tension, okay? If I start, and at this end, at the other end, sorry, I'm just gonna hold it in place. I'm not really gonna do anything. So you can't really see it, but you can imagine if I'm pulling at this end, then at this end, I kind of have to pull back in order to keep this ruler from moving. If I start pulling at this end, but I don't do anything at this end, I just kind of let it slide through my fingers, I mean, you probably guess what's gonna happen. It'll move, right? It won't be in equilibrium anymore because, you know, I'm putting a force on one end, but I'm not balancing it with another force at the other end. So it'll just move out of my hand and it's no longer in equilibrium. And again, it's obvious, but remember, we're talking about equilibrium. So if you notice, while you're doing your calculations, that something isn't adding up, that means, well, that means you made a mistake because we're not talking about things that are moving. And then, you know, same thing the opposite direction. So let's say at this end, I start pushing in. Then at this end, what's gonna happen is as I start pushing in, at the other end, I kind of have to push back in to keep the ruler in equilibrium. And again, if I start pushing on this end and then at the other end, I can't do anything, it's just gonna move, right? So basically what I'm trying to get at here is a two force body is always entirely in tension, meaning you're pulling on it, you're stretching it out, or in compression, meaning you're pushing it. Also, by the way, this thing is obviously bending. The two force bodies talking about in our mechanics problems are assumed to not bend, be weightless, be like, basically they don't move at all. So pretend this thing isn't bending, it's only bending because, you know, it's a thin ruler. So yeah, if you have a two force body with a pin connection at each end, and you find out that at one pin connection, so let's say this one, it's in tension, right? The two force body is being pulled. That means at the other end, it must also be in tension. It cannot be in tension at one end and in compression at the other end. I mean, I could show a demonstration. I'll pull away at this end and then I'll push in on this end again. You can probably guess what's gonna happen. It's just gonna move, right? Because it's not in equilibrium. The forces do not add up to make sure this thing doesn't move. So yeah, that's a very important thing to understand, right? So if you calculate the force of a two force body at one pin, then you know at the other pin, the force has to be exactly the same magnitude, right? Because if let's say I, you know, pull at this end with 100 newtons, but at this end with only 10 newtons, it's still gonna move, right? Because the force at this end is greater than the force at this end, it's not equilibrium. So yeah, you know that the reaction at the other pin has to be exactly equal in magnitude and also exactly opposite in direction. So let me show some demonstrations to explain what I mean by that. So let's say, you know, at this end, let's say I pull up at this end with like 100 newtons. And then at this end, I'm going to pull down with 100 newtons. Now you might think, okay, maybe it's balanced, right? Because it's 100 newtons up, 100 newtons down, that adds up to 0. But I mean, you can probably see what's going to happen here. It's going to rotate, right? Because I'm pulling up at this end, so I'm pulling it up, and then at this end I'm pulling it down. It's going to rotate, and then it's going to stop rotating once it's in equilibrium. Once the forces are perfectly balanced. Yeah. Up here, the force is exactly 100 newtons up. Down here, the force is exactly 100 newtons down. So now it's in equilibrium. So basically, that kind of gets to my second point, which is that, I mean, it's basically just the first point, just a little bit reiterated. Any force at one of the pin connections at a two-force body, its line of action has to go through the other pin. There's no exceptions, right? Sorry, I got interrupted for a second. So what I was saying is that if you have a two-force body, right, so it has a force at the pin connection at each end, the force at each pin, so let's say the force at this pin, its line of action has to go through the other pin. So if, for example, let's say, you know, this two-force body, okay? So the first force is my hand pulling up, and the second force is just gravity pulling down, right? The force that my hand makes to pull up on the ruler and keep it equilibrium has to go straight up, right? If I start, you know, if this force at my hand isn't straight up, if it's, you know, to the side or whatever, then obviously it's going to start moving. For it to be in equilibrium, this force has to go straight up. Now, and of course, the force of gravity has to go straight down, right? So what does that mean? If the ruler is pointing straight down and my hand is pulling straight up, the line of action of the force from my hand goes straight through the ruler all the way to, you know, the other end, all the way. And let's just say, you know, for this demonstration, let's assume that the weight of the ruler is a pin connection, or even I just put my hand here, right? I'm pulling down with my hand here, I'm pulling up with this hand, right? The force from this hand is going straight up, and its line of action goes straight through to the pin connection at the other end of the ruler. And same here, right? I'm pulling down at this end, I'm pulling straight down. And so the line of action of its force goes straight to the other pin. And that is a thing that always happens in two-force bodies. If you have a two-force body, then the reaction at one pin has to go through, like the line of action of the reaction at one pin has to go through the other pin connection. And same thing at, you know, the other pin, obviously. So basically, that's just another way of saying they're equal and opposite, but it's a bit more concrete. So, you know, let me just give like another demonstration. If I, at this end, let's say I pull diagonally. Let's say I pull, you know, up and to the left, and then at this pin, I'll pull down and to the right. So up and to the left, down to the right, you can probably guess what's going to happen. It's going to rotate. Also, by the way, guys, sorry if like my left and rights are wrong. The camera's mirrored, so if you're getting confused, just, you know, just follow the directions that I'm drawing with my hands. So yeah, as you can see, I'm pulling diagonally up left here, down right here. And so the line of action of each force has to go through this ruler to the other pin. And it's the same case at both pins. It'll always be that way. And you might think, what happens if it's not that way? What if, like, you know, I mean, I actually already showed the demonstration, but I'll show it again in the scope of what I'm talking about now. If I, you know, let's say I pull up at this pin, and at this pin I just move to the side, right here, I'm just going to pull to the side. What's going to happen? It's going to rotate. And the thing is, it's going to rotate until the force from this hand goes through the ruler. So that's a thing that's like another thing that's really important to remember, probably, you know, equally or maybe even more important than my first point. I'm going to show like another demonstration just to make it a bit more clear why this matters. So, okay. So hopefully you guys can see this. It is a clear ruler, so it might be kind of hard, but bear with me. So as you can see, it's one of these like L-shaped rulers. Let's pretend for the sake of the demonstration that this part, the hypotenuse, does not exist. So we're talking about an object that is just like the shape of an L. And I'm gonna pin it here. I'm gonna put one pin here, another pin right here, okay? And I'm gonna start pulling to the side. So here I'm just gonna pull straight to the side. Here I'm also gonna pull straight to the side. And watch what happens. It's pretty, I mean, it might be obvious, but it's pretty important to understand. So as I start pulling, as you can see, it rotates. It rotates until it's in equilibrium, right? It's no longer moving. And it rotates in such a way that now the force from each of my hands goes through this diagonal part. But again, pretend this diagonal part doesn't exist. So basically, what I'm trying to show here is if your two-force body is a straight line, like this ruler, then the forces will always go directly through the body, if it's a straight line. However, if your two-force line is not, or sorry, if your two-force body is not just a straight line, if it's like an L shape or something like that, the force at each pin will still just go through the other pin, no matter what. So if you had an L shape, again, pretend this diagonal part doesn't exist, then the line of action of the forces will actually go out of the body into the other pin. And that will always be the case. You cannot, again, if you don't have that, then it just won't be in equilibrium. It'll start rotating. And it'll rotate until it's in equilibrium. And of course, we're only talking about equilibrium. So that is another really important thing to understand. Why does that matter? Well, okay, so I have this demonstration drawn on the board here. It might be kind of blurry on the camera. It doesn't really matter. Basically, what you can see here is at the connection, I have reactions. And the thing is, we always break reactions up into X and Y components, right? And that's for convenience sake. You know, you can only analyze forces in X, only analyze forces in Y, and it makes things really easy. The thing with a two-force body, however, is because you know where the pins are, and you know that the force has to go through the two pins, you don't have to break the force of a two-force body up into two parts. You can simply use the fact that you know the angle of the force because you know where the other pin is and where the force is going in order to only have one unknown. So here you have two unknowns, right? Because you broke up into X and Y. But if you have a two-force body, you don't have to break it up into a separate X and Y. You can just use the one unknown of the magnitude of the force in the two-force body. And that's really helpful. That's like super important. There's a lot of questions in our midterms that are, I wouldn't say necessarily impossible if you don't understand that, but really hard. They become very difficult because then you have way more unknowns, you have to use way more equations, you probably have to break your bodies up in like complex ways. So basically, understanding that, understanding that two-force bodies do not have to be broken up into X and Y components is like super crucial.
Okay, so now I just want to go through one of the questions from the practice exam and kind of show what I did,
why I did it, and why understanding how two-force bodies works is really important for this question. So this is question 2 from the winter 2022 exam. What they're asking us to find here is the forces at the pins in D, E, and F on member DEF. So basically we're considering the DEF is our, the part that I care about the most. So I want to get ahead here and drew the free body diagram of the entire member. That's what you're usually going to start with. You're usually going to start with looking at the entire member in order to find reactions at pin connections, like pins that are connected to the outside, basically, of the member. So in this case, we have two pin connections right here, RCX, RCY, and then RFX, RFY. So we have 4 unknowns right now. Obviously, we do not have the capability to find all of them. That's too many unknowns, but we can still find one. So we can't do force balancing in X or Y because obviously there's 2 unknowns in each. So instead, what we're going to do is we're going to find the moment. And we're going to do it around C. The reason why we're going to do it around C, so first of all, it eliminates both the reactions at pin C. It also eliminates the x component of the reaction at F, since they're at the same level. So the line of action of R of x goes, let me use a different color. It goes, it goes straight through C, meaning that the moment that R of x produces around C is 0, so we don't have to consider it. So basically, if I find the moment around C, the only unknown left in the equation is R of y, so you can find R of y. You could also do the moment around F, and then you can find RCy. But the thing is, in this question, that's not really helpful because, like I said, the question is asking us to find the forces in DEF, so there's not really any point of finding the y component of the force in C, since that's part of CBA. So it's the equation, very straightforward. The 100-pound force, that's what's given to us right here. It produces a negative moment around C, which you can see like it rotates around clockwise, which means it's negative. So it's negative 100 pounds times 45 inches, that's just the distance given. Plus we have R of y times 20 inches. R of y produces a counterclockwise moment, so it's positive. Rearrange the equation, we get R of y is equal to 225 pounds. Now we assumed at the start that R of y goes upwards, right? And that assumption turned out to be correct, which is why R of y is positive. If we assumed R of y to go downwards instead, then we would have gotten a negative value for R of y. It would have been the same value. It still would have been 225. It just would have been negative. So because we would have assumed it went downwards and we got negative, we would have to flip the direction. So it would still be 225 upwards. You would have gotten the exact same answer. So now we have that unknown. Like I said, we can now solve for RCy, right? There's only two forces in the y direction. So RCy would be the only unknown. But we don't need that. We can't solve for RFX because we have two unknowns in the x and we can't isolate one of them with a moment. Like I said, they are on the same line of action. So like if you took the moment around C, you would eliminate both of the x components, and if you took the moment around F, same thing. So we can't find RFX now. So what we're gonna do is we're going to look at just DEF on its own. And this is where two force bodies come in. Actually, I forgot something. The first thing you should do for any of these questions is you should identify where the two force bodies are. So hopefully you guys can see which members here are two force bodies. The first one is A and D. And the reason why is because it only has two pin connections. And you might be thinking, okay, but what about this force right here, this 100 pounds? Isn't that another force? There's a reaction at D with DEF. There's a reaction at A with ABC, and there's also the 100-pound force. So doesn't that mean it's not a two-force body, it's a three-force body? But when we call something a two-force body, what we're talking about is the body itself. We're talking about AD. And AD only has two pin connections. Those pins can have, 100 forces on them. They could have as many forces as you want. But the pin itself is still, those forces all combined is just one force. The pin itself is still just one force. AD only has two forces on it, the pin at A and the pin at D. The reactions out here don't really matter to the actual body itself. It's still just two forces because it has two pins. Maybe that's obvious, maybe that makes sense to you, maybe it doesn't. If it doesn't make sense to you, don't worry about it. Just remember, if a member only has two pin connections, it's a two-force body. If a member has more than two pin connections, so for example, ABC has three pin connections, right? It has the pin at A, the pin at B, and the pin at C, then that's not a two-force body. That is a three-force body in this case. Same with DF, it has three pin connections, so it's not a two-force body. If it has two pin connections, it's a two-force body. Otherwise, it's not. So in this case, yeah, there are two two-force bodies in this whole thing. There's AD, because it has two pin connections, and then there's BE, because it also only has two pin connections. So what we're going to do now is we're going to draw another free body diagram of just DEF, because that's the one we're considering for this question. Like I said, they want us to find the forces in DEF. If the question asks us to find the forces in ABC, we will draw the free body diagram of just ABC, but for this particular question, it's unnecessary. So here's the free body diagram I drew of DEF. So as you can see, RFY, since we found RFY, I replaced it, or I just put it what it actually is, 225 pounds upwards. We still have RFX unknown, right here. The unknowns like are red, in case you guys haven't noticed. I've been drawing those in red. And then we have these two forces from the two pins, from BE and AD. But they are two force bodies. And like I said before, because they're two force bodies, we know the exact direction that those forces are going in. So we don't have to break these two reactions into X and Y components. We can just consider them as one force, and we know the exact directions because if we look at the original drawing, we know this is 20 inches, this is 15. And so we know that this force, for every 20 units it goes to the left, it goes 15 units up. And then using Pythagorean theorem, we can find that the combined magnitude is 25. And it's the same thing for this one. And so because of that, instead of having 5 unknowns, right, if we broke these up into X and Y components, we would have R of X, we would have the X component right here, and we have the X component right here. Plus then we would have the Y component here, and the Y component here. We'd have 5 unknowns, and you can't really solve for 5 unknowns. That'd be really hard. Technically, I think you maybe could if you like made a bunch of equations and combined them or something. Maybe, I don't know, but in general, you can't do that. So by doing this, we can turn the two force bodies into just a single unknown, each of them, and that makes things way easier. That being said, looking at this right now, there's not really a very obvious way to solve this. You know, if you take the moment, let's say you take the moment around F, you still have 2 unknowns, FEB and FDA. If you solve for like the X components, then you have 3 unknowns. You have the R of X, you have the X part of FEB and the X part of FDA, so that's still 3 unknowns. And if you solve for Y, then you have 2 unknowns, FEB and FDA. So right now it kind of looks pretty tricky. Like, how would you find, how would you solve this? But there is a way. And the way is what we're going to do is we are going to take the moment around X. And in this case, X is off of the body. This is, this can seem like a bit of a confusing concept. How can you take the moment of a body outside of the body, right? Because X is not connected to it. X is just like, if you look at the original diagram, X is literally like over here somewhere. It's just like nothing, it's air. So that might seem a bit strange, like how can we take the moment around X if it's not part of the body? Basically you just can, like, honestly, even I don't know how exactly it works, but you just can do it. If that makes sense to you, great. Like if you understand why that works in real life, great. If not, then all you have to do is remember that whenever you're looking at a member, you know, and you have a free body diagram, you can take the moment from anywhere. You do not have to take a moment from on the body. You can literally take the moment from any point. Usually we take the moment from on the body because in general, the forces are on the body. And so by taking it from on the body, you can eliminate unknowns. So for example, at the first step here, we took the moment around C. By doing that, it eliminated RCX and RCX and RCY immediately, since those forces go straight through C. But like, you don't have to do that. You could take the moment. I could take the moment around like right here. It wouldn't eliminate any unknowns. That'd be pretty useless. But you can do it. You could take the moment like, you know, anywhere. You can take the moment from anywhere. You just have to know the distances. So that's what we're going to do here. We're going to take the moment around X. And the thing is, we know exactly where X is. So X, okay, what is X actually? Let's talk about that. X is the intersection of the line of action of R of X and the line of action of FEB. And why is that helpful? Because if we take the moment around the intersection of these two lines of action, both this force and this force are not in our equation. They get eliminated, right? Because their lines of action are going through X, meaning that the distance, because you know in moment you always use force times distance, the distance will be 0. So we don't have to consider these forces, and then the only unknown we have is FDA. And the thing is, we can figure out where X is because we know the exact direction that FAB is going in. Since it's a 2-force body, we know that it's 20 here, 20 to the side, 15 up. And so we can find it right here. We know this distance is 15, right? That's just, that's given in the question. We know that distance is 15. And we know that this force, for every 15 that it goes up or down, it goes 20 to the side. So we know that X has to be 20 to the side. And so that way, we know exactly where x is. It's 20 inches to the right of the body, and it's 15 inches down from point E. And so now we can find moment around x. So that's what I did right here. So first we have this 225 pounds, right? That's the R file we found earlier, and it is going clockwise around x, which means that it's negative. Next, we have the FDA in y. So, okay, I've been saying that, we're not breaking the forces up into x and y components. We technically are, it's just they're not separate unknowns. In this case, the y component is just the full force of FDA times 15 over 25, right? Because we know, well, that's just because, 15 over 25, that's opposite over hypotenuse, which is sine theta. Hopefully you guys know that. So we know how much FDA goes up, or like how much the vertical component is. And then same thing, right? And it's of course by 20 inches because that's the perpendicular distance. And then FDA in the x direction, well, that's 20 over 25 times 30 inches because that's the perpendicular distance. And so with that, we can find FDA. Now, one important thing to note, for these two force bodies, in general for two force bodies, you always want to start by assuming their intention. So their intention, they are pulling away from the body you're considering. They are going away. And if that doesn't make sense to you, think about having a rubber band between your, wrap a rubber band between your finger, around your finger, and then pull on the other side. It's going to pull on your finger. The rubber band is pulling away from your finger. So the force it produces goes away from the body. So we assumed that FDA is intention, and because at the end FDA is positive, that means our assumption was right. FDA is in fact intention, which means it is in fact going in this direction. So now that we have that, we can find the other unknowns. We can find FEB just using, because now the only unknown in the y component is FEB. We know FDA, so we can use that in the sum of forces in y. We of course know this 225 pounds. And so now the only unknown in y is FEB. So this is the equation right here. So we have 225 pounds up. We have 375 pounds up, which is, sorry, 1 second, what is this? Oh, I made a mistake here, sorry guys. This should not be 375 pounds up. This should be 375 pounds up multiplied by 15 over 25, right? Because we're only considering the vertical component of FDA. So this should actually be 375 times 15 over 25. There we go. And then FEB, again, we're assuming it's intention, so we're assuming that the vertical component is upwards, right? Because if it's going up left. We multiply by 15 over 25 because, again, we're only talking about the vertical component, and we get FEB is equal to negative 750. Now, this is important, negative. So we assumed FEB was intention. However, at the end, when we actually found FEB, the value is negative. That means FEB is actually in compression, which means that its force is going into the body. It is going into the EF. So yeah, it's the opposite of tension, right? That's one way to think about it. Another way to think about it is I don't know, let's say you take a sponge, right? And you compress it down. The sponge, with your hand, the sponge is gonna push it back on your hand, right? It is pushing into you. So in this case, FEB is compressed, so it is pushing into DEF. And that is the assumption we made. And then one more thing. Now the only unknown is RFX, right? We found FEB, we found FDA, now we just need to find RFX. So for that, we do summation of forces in the x direction. So first we have negative 375 times 20 over 25. That is FDA. We know that FDA is in tension, which means it's going in this direction, which means the x component is going to the left. And I'm sure we all know x to the left means it's negative. So that's the first part. Second part here is 750 pounds times 20 over 25. That's what we found right here, FEB. And we know FEB is in compression, which means it's going into the body, which means the x component is going to the right. So it's actually positive, as you can see, plus. And then RFX, we say plus RFX. We're assuming RFX is going to the right. That's what we've been doing the whole time.
And then we got RFX is negative 300 pounds. So actually RFX is not going to the right, it's going to the left. Because we got negative, that means our assumption was wrong. RFX is actually going in this direction. And with that, this question is solved. I do want to talk about one more thing that's very important to understand. It doesn't matter for this question, but for other questions, it would be pretty crucial. So like I said, we found that FDA is in tension, and we found that FEB is in compression. So if we go back to the full free body diagram, so FDA is in tension, which means it's pulling away from DEF, while FEB is in compression, which means it's pushing into DEF. Now, but remember what we talked about before. The entire two-force body is in tension, right? The whole thing has to be in tension. You cannot have a two-force body that's in tension at one end, but in compression at the other, because then it won't be in equilibrium. Then, you know, you guys saw my demonstrations, it'll move. And same thing with this one, right? If it's in compression at E, it has to be in compression at B. That means if we had to solve for the forces in ABC, we don't have to for this question, but let's just assume we have to. The force of AD will actually be going this way. And the force of BE will be going this way. Because AD is in tension across the whole body, BE is in compression across the whole body. That means that the reactions are equal and opposite at the two different points. Sorry, two different pins. So remember that, right? That's something that I feel like people make a mistake on a lot. They find the force at one pin, and they assume the force at the other pin is the same. So they would assume that because here it's going to up left, here it should also go up left. But that's not how it works. Remember, two-force body, the entire thing is either in tension or the entire thing is in compression. You cannot have it be in tension at one point of the two-force body and then in compression at the other point. At least for, you know, what we're talking about Civ 105. Obviously in the real world you can have, you know, let's say for example the density of this half is like way higher than the density of the other half, then the forces get a bit different. But we're not talking about that for this Civ 105 midterm. We're just talking about a weightless two-force body that's I believe the term is consistent across the whole body, meaning, you know, or sorry, the density is consistent, which means that, like I said, tension at both pins, compression at both pins. You cannot have tension at one and compression at the other. So hopefully this helped. Okay, one more thing I wanted to talk about. So we were just talking about how, you know, two-force body, if I find that the reaction at this pin, you know, is in tension, right? It's pulling away. That means that here it must also be pulling away, right? Because the whole two-force body is either in tension or, like in the case of this one, the whole two-force body is in compression. So it would be put onto DF, it would be pushing in, and onto ABC, it would also be pushing in. And so when you're talking about the reactions of the, or like the forces that the two-force bodies apply on these other bodies, right? That's how it works. Tension pulls away. However, if we're looking at the two-force body itself, right? If we're actually looking at what's going on inside this two-force body, and this two-force body is in tension, the forces inside are actually the opposite of the forces that we found as the reactions on DEF and ABC. Now that might sound a bit complicated. That might sound a bit weird, like how are the forces opposite? But let's, I'll try to explain it from two different angles, so hopefully it makes sense. So first of all, let's just consider this pin, right? Just the forces on the pin. We're not considering like any of the members, any of the bodies. We're just considering the forces that are on this pin. So we have the force of the tension, right, that we found, like the force that this two-force body is applying at D. But the thing is, D cannot just be like this, right? Because this is not equilibrium. This pin is not in equilibrium. In real life, this pin would move. I don't know exactly how that would work for this body, but I guess the whole thing would probably just collapse. So that means that another force has to balance it, and that force is the force of the two-force body. Again, that probably sounds, and that might not make sense. Even to me, that's kind of a bit complicated. So let's just think about, you know, a practical example. This thing is in tension. Let's pretend you have a rubber band between your two fingers, or maybe even go grab a rubber band if you have one. I don't have one. But let's pretend you have a rubber band between your two fingers, like let's say the index finger in each of your hands, and you start pulling the rubber band apart. So the rubber band is in tension, right? At each of your fingers, let's pretend that this pin is one of your fingers and this pin's the other finger. At each of your fingers, the rubber band is pulling your fingers into the middle of the band. It's trying to pull them back together, right? Because in tension, it's trying to pull your fingers together in order to like not be in tension anymore, right? That makes sense. But the rubber band itself, the rubber band itself is being stretched out, and it does not want to be stretched out. It wants to go back to, being normal. And so what that means, if you think about what that means, basically you're stretching out the rubber band from, let's say from the middle. That means you're pulling on it away from the middle, right? You are taking this rubber band, which wasn't stretched, and you're pulling on it from the middle, right? Because you're pulling out at each end. The middle is like, you could say the equilibrium point or something like that, or the center of gravity, and you are pulling away. And so the forces inside the rubber band that is in tension is actually going away from the middle. So hopefully that kind of makes sense. I don't think this really matters. I don't think there's going to be any question that asks you to analyze the forces inside a two-force body. But just in case, that's, I think, important to understand. And then let's also consider this one. This one's in compression, right? And so in this case, let's consider, a sponge. You have a sponge that you're squishing between your two hands. So a sponge itself is pushing back on your hands. It's trying to make your hands move apart so that the sponge can stretch back out since you're compressing it. But the forces inside the sponge itself, they're going like this, right? Because you're taking this sponge that was normally, let's say, let's just say it was normally 10 centimeters tall, and you're compressing it down to only be like 2 centimeters tall. So what that means is you're pushing into the middle of the sponge. You are making it smaller, and the forces inside the sponge are pushing into the middle. So while the reactions, again, the force of BE at pin E on DEF is pushing into E, the forces inside the two-force body are actually going into the middle of BE, meaning away from E. So again, I don't know if that matters for sure for the midterm, and if this confused you, you can totally ignore these last 5 minutes. Just don't worry about it. I'm pretty sure we won't have a question like that on the midterm, but just in case, hopefully that helps you understand a little bit more how these things work. Okay, so I actually wanted to show one more quick thing. So this is just a example of a possible problem you could run into in one of the practice questions. This actually comes from question 1 of the winter 2024 practice exam. So this isn't just like some esoteric example I came up with. This could actually happen. So what we're doing here is we are analyzing the forces at a single pin, right? So we have the pin in the middle, and then we have all these different forces coming out of it. So we have this 3 kilonewtons down, we have these forces, and then we have these 2 unknowns. We have FGF and FGD. FGD I circled in pink because that's the unknown that we actually care about. Like that's the one we want to solve for, but they're both unknowns. We don't know the magnitude of either of them. And looking at this, you might be a bit confused how to solve it, because the thing is, if you take the net forces in the F, we have 2 unknowns. We have the X part of FGF and we have the X part of FGD. And then if you take the net forces in the Y, you still have 2 unknowns. You have the Y forces of FGF and the Y forces of FGD. So, and the thing is, obviously, because this is a pin, because we're looking at a single pin, you can't take the moment either, right? Because if you took the moment around the middle of this, then everything goes through it, so you just wouldn't get a moment. And then if you took the moment somewhere else, like say right here, then you would still have 2 unknowns. Technically what you could do, I guess in theory, now that I think about it, is you could take the moment, let's say right here, along the line of action of FGD, and then FGF would be the only unknown, but that would be really hard. You'd have to find all these different perpendicular distances to that point. That would not be an easy solution. There's a much easier way to do it. So we have these 2 unknowns, but the thing is, we know all the angles. We know the angles between all the different forces. They're not given in the original question, but you can find them pretty easily with some trigonometry. And so we know all of these angles. And so what we can do, I'll show you right here, is we can actually rotate the whole thing. We can rotate all the different, like basically you can rotate the pin. So compare what happened here to what happened there. Basically FGF, as you can see, I rotated it 30 degrees upwards. And of course I rotated everything else too. So FGF goes 30. This 1.732 goes 30 in this direction. This 5 goes 30. And then this one also goes 30. So I rotate the pin. And now with this rotated version, you can see if we take the net forces in the y direction, then FGF isn't even considered because it's completely horizontal now. We only have one unknown in the y, which is FGD, and that's the one we were trying to find. So now if you took the net forces in y, you can find FGD, and then also if you wanted to, after that, you could also take the net force in x and find FGF. We don't have to do that for this question, but in general, you could also do that. So yeah, this is something to consider if you ever end up in a situation like this where you have a pin that has two unknowns coming out of it, like two unknown forces, and they both have x and y components. You can just rotate the pin so that one of them only has an x or only has a y component, and then you can solve for the other one. There is one situation where this doesn't work. So let's let's just pretend this FGF isn't here. Let's say the first unknown is FGD, and then the other unknown is like this, and it's perfectly 180 degrees opposite of FGD. In this case, this strategy doesn't work because the thing is, if you rotated this, if you rotated it, in this direction, then they would both just be perfectly vertical, which means if you took the if you took the vertical components, you'd still have two unknowns. And if you took the x components, they would both be eliminated. You wouldn't be able to solve. And then same thing if you rotated it to be perfectly horizontal. If you took the x component of that, then you'd still have two unknowns. If you took the y component, they're both perfectly horizontal, so there's no unknowns. So in this situation, if your two unknown forces are perfectly like 180 degrees to each other, then in that case, this strategy doesn't work. But otherwise, you can just do this. And then you can find, if you have two unknowns, you can find one. Or I guess technically you had three unknowns. Let's say you had a third unknown that was like this. This one right here. This would still work. You'd still find FGD because FGF has no y component, and then this other unknown also has no y component. And then you can find FGD. So yeah, that's just something to keep in mind if you're doing, this would be helpful for like the question ones in all our midterms, the one where you're analyzing a truss. And if you're looking at a single pin, you could do this to find the forces at that pin. So hopefully this helps.